starting, because otherwise he will make grumpy face at me. Hello, everybody. It is now 10 a.m. Welcome to IEPG at IETF 125. Does the clicker works? So this is what the IEPG is. It was originally created by RFC something or other, like 16 something something, written by Jeff. So it has been running for a long time. It's supposed to be topics of operational relevance in some form of fashion. Um, for some reason this time, it is all DNS. We seem to go through cycles where the entire IPG agenda is BGP. Sometimes it's all DNS. Probably it's all DNS because DNS is the best protocol there is. BGP is a close second. And this is our agenda. Um, it's going to be, as I say, all DNS. So I'm Warren. Jen, unfortunately, is remote this time. So she can't sit up here and make sure that we stay on time, but she says that she will poke people if they run late. And I will end my talk now so Job can officially agree that we are actually under time. I will hang up and we will have Willem present on global local route. Would you like to use the clicker? There we go. Is there a red box? Yep, there's a pink box. Oh, actually, just before we start, does anybody have any technical issues? Is everything working correctly? Everybody can hear us? If people can't hear us, they don't know that I said that, so I guess we'll just assume it's good. Take it away.
Okay, so this is about, or the motivation for this research is the local route best common practice draft from Jeff and Warren and Jim Reed, etc., which is a proposal to provision resolvers with the root zone, which has all sorts of advantages. I'm a big fan myself, actually. And at NLNet Labs, we are close to the University of Amsterdam. They have a security and network engineering master, and they do short research projects, like for 2 weeks, so to say, 1 week to make a proposal, 2 weeks to do the research, and then 1 week report. And so I thought it would be a good idea to have a look if this proposal to make this best current practice would be deployed at scale, if that would impact the traffic on the internet, if it would make it larger or smaller, and if so, how much. And so this research was executed by Ilyas Rahimi, and this is his report. You can find the report on our website as well. So the method he employed was to first define what traffic is. So in this research, we define traffic to be the bytes transferred per resolver per day. And then the experiment or the research was a very hands-on practical thing, is to set up existing open source resolvers with the example configuration of version 1 of the draft. I noticed that in version 2 and 3, the example configurations are no longer there, but and then measure the traffic between the resolver and the root, and in some cases, the root is provisioned by downloading the root zone from internetnic.net. So to measure the traffic towards that site as well, and compare that to a baseline. So how to get a good baseline? Well, there is the fantastic, amazing RSEC 002 report, which is advisory on measurements of the root server system. It's basically root server operators reporting, measuring their own operations and publishing statistics or the metrics that they measure. And one of those metrics is the number of unique sources seen at the root server identifier, uh, the number of unique IPv4 addresses and the number of unique IPv6/64 networks. And so that could be considered as the number of resolvers seen as a resolver or a root server instance. So the measurement is sort of rough estimation of what traffic would be, of course. And we then only need the traffic per day at such a root server instance to be able to determine the traffic per resolver per day. And unfortunately, that metric is not available with our SEC 002 data, but there is the query and response size distribution, which is published as a list of ranges with per range the number of requests and responses for TCP and UDP and queries and responses. And so if you multiply that number of requests and responses per highest number of that bucket, then you do have some sort of rough estimation of the traffic of that root server instance per day. So divided by the number of unique sources seen at the root server instance would then result in the daily traffic at resolver for that root server instance. So here's the results of the baseline. Well, not really a measurement, but applying this idea to the root server identifiers. And so they all sort of lie in the same number range, around 1 megabyte per resolver per day, except for F. I think this is probably a mistake. There's probably the number of unique sources isn't the actual number of unique sources. So Ilias left F out of the further evaluation of measurements. And here are the results for the different resolver configurations, how much traffic that they used towards the queries and responses towards the root servers and also towards Internic. And so the first one is bind with the plain DNS transfer. You see that it also, yeah, the root zone updates at least twice a day and sometimes 3 times a day if there's a change, sometimes 4 times a day, but on average 2.5 times. And a transfer with bind takes around 1.45 megabytes. The wire format zone transfer, so the total megabyte per day is a simple multiplication of the number of updates times what the transfer costs. The same holds for Unbound, though it uses a little bit less surrounding queries towards the root server to look up the addresses, for example, to where to transfer the root from. But one of the surprises from doing this measurement plane was Unbound fetching the root zone over HTTPS, because it had 48 updates per day instead of 2 or 3 or 4. And and also over HTTPS, the root zone is in presentation format. So it's 2.2 megabytes instead of 1.3 in Y format. So that resulted in 105 megabytes per day for Unbound. Also not resolver was sort of different. Also gets the root zone over HTTPS, but pre-fills its cache with it. And it has a scheduled period to fetch the root zone, and it transfers only once a day. So it's once a day, a bit more than the 2.2 of Unbound because of the way not resolved does priming, etc. Yeah, so this one is a nice outlier that needed further investigation. So this is because Unbound considers, if it's configured like that, uh, the Unbound thinks it should serve the root as a secondary authoritative service. That means that it should adhere to all the values in the SOA records. So in the SOA record for the root zone, it says, check if there's a new version every 30 minutes. And over DNS, this would be a DNS query for the SOA record. And then the resolver would know, oh, there's no new version, so I don't need to transfer the zone. But this logic was just there in Unbound, and the mechanism to transfer the root zone was just the same as with normal DNS transfer, only then HTTP. So it would just blindly transfer the whole zone every 30 minutes because it cannot do a DNS query over HTTPS. Unbound did not yet have support for ETAG and if non-match mechanisms, which is a HTTP mechanism to check if a version of the file you're requesting has changed. But yesterday I managed to implement this, luckily, and it's available. It's that pull request, so I assume the next version will no longer do this. So the further measurements from Ilias are also considering Unbound with the bug fixed, so to say. So not resolver updates once a day, which is also different from the other cases. And so it doesn't consider the SOA for its timings. And maybe that's a reasonable thing because the SOA is not for resolvers, it's for authoritative name servers. And the lowest TTL in the root zone is actually 1 day. So there would be no need. So apparently the root is fine with resolvers having maximally 1 day all data, right? Or at least that would be a point of view. Yeah, Ilios also made this picture, which is nice. It's on logarithmic scale. So the upper line is 100 terabytes per day. More traffic, I think. But yeah, so with current, how resolvers currently operate, not resolver would do best by just fetching it once a day. But all of them, it means more traffic per resolver per day. But so currently the root is fully signed, plus minus 2.5 times a day at 4 a.m. in the morning and 4 p.m. in the afternoon. And when changes happen, so that explains sort of what the daily traffic would be. But fully signed means that there is no incremental transfer because in an incremental transfer for the root zone, first all the signatures would need to be removed and then replaced with all the new versions, and the size of 2 times the size of all signatures is larger than the size of the whole root zone, and therefore the transfer is always full. Is a full transfer always. And so we ask ourselves the questions, what if it would have been incrementally signed, which means that a portion of the older signatures is renewed twice a day, and only the changes are re-signed when changes happen. So you need to do this properly. So it would be bad if signatures would expire and the zone itself is not yet expired. So it's important that the signature lifetime is longer than the expiry time. So that means that there need to be every signature needs to be renewed at least every 6 days. And so since it is resigned twice a day. We've incrementally resigned the route for 1/12 of the portion of signatures, twice or every time the route updates. And we sort of maintained a shadow version of the signed route, and you can have a look at the files itself at this GitHub repository, which has all the versions of the route zone since the 22nd of December. And it also contains presentation format of the incremental transfers of one version to the other version. So here's a picture of that repository. The .zone files are the zone files for that version, the .ixfr files, the presentation format incremental transfer files. And here you see in the incremental transfer file, the presentation format, that it also mentions how large it is, how many bytes. So, you can just, if you check out that repository, do a simple grep for data size and get an indication what the incremental transfers, how much that would cost the resolver. So if we put that into that same table, 2.5 times the average change or size of the change, then you would end up with daily traffic which is actually lower than the baseline, than what we estimated to be the current daily traffic average per resolver. So that's it. We also are developing a new DNSX signer at Nelnet Labs in Rust. And there's also a command line version testing out things, which is called DNST. So there's the branch where you can check out that command line tool to incrementally sign zones. And there's also a script to create incrementally signed versions of the route. Yeah, I don't know. I haven't looked at the time myself, but some discussion points could be, does traffic size matter? Or with respect to timing and refreshing, what would make more sense? The SOA, which is intended for authoritative name servers, or TTLs. What do you think?
Job Snijders, BSc Software Development. What I think,
Yeah.
you should go back to slide 7, please.
Slide 7? Which one is that?
7. It's between 6 and 8.
Yeah, but there are no numbers on the slide.
Oh, there is in the. If you
I did
go back a little bit to the tables of not and unbound.
Oh, okay. The published tables. This one.
Yeah.
Okay.
The lower left, 2.19 megabytes per update.
Yeah.
To me, it smells like you desperately need gzip compression in the HTTP layer.
Oh yeah.
Because then it's 950 kilobytes. So you can take this idea to shave off 56% for free, and it's better for the environment that way.
Yeah, good point.
But more importantly, using compression will increase the reliability of the transfer, because your transfer is shorter and therefore a little bit less susceptible to packet loss.
Absolutely.
So
Absolutely.
that's what I thought. Thank you for the presentation.
Good point.
Hi, this is Dwayne Wessels from Bearsign. Thanks, Willem. One concern I kind of have with the comparison is that you're comparing real world data with kind of an idealized behavior of local root, right? We know from lots of previous research that 90+% of the queries to the root servers are junk. They shouldn't be there, right? So these are misbehaving clients. They're doing something that we don't expect outside of the protocol. And so you're comparing that to something that doesn't exist yet.
Yes.
And certainly I think we should expect that there would be misbehaving local route implementations that would do the same kind of things, send excessive amounts of traffic. And so I think this comparison is a little bit unfair in that regard.
Absolutely. There is yeah, we assume a lot of things, like all the resolvers will do aggressive NSEC, for example, and yeah, there will be no queries to the root server, which is absolutely not the case. Yeah,
Thank you.
clear. So it's just a rough estimate.
Rafeva Akamai. So one of the things I have a question on is the amount of traffic you consider that a resolver sends to a root server, but a resolver normally sends traffic to root servers.
Yes.
So can you go back, I think, 2 or 3 slides?
Go back,
Go forward.
forward, 2 or 3.
This no one.
This
more,
one.
one more.
One more. Okay.
So you say the daily traffic is roughly 9.069 megabyte, but that's
Yeah.
to one root server, right?
Yes, that's the average of the root server instances. You mean the baseline?
The baseline.
the baseline.
I'm questioning the baseline because resolvers will ask more than one root servers.
Yeah, yes, but yes, that is true. But so also those resolvers will be seen and reported in that same RSEC data as a unique source. So the actual amount of traffic at the root server instance and the number of unique sources seen would sort of match on average if you take the whole root server system.
But that, I mean, each source would then still be present in 2 kind of like different root servers.
Yeah, but they will also do queries to those 2.
Yes, that's why I mean the resolver will query more than the 0.96 megabytes.
I don't think so, but yeah.
And overall, I mean, what is the overall total traffic we are talking about here? Because that's, I think, also something to consider.
Yeah, so maybe you walked in a little bit later, didn't you? So I have actually a slide of how to the baseline was determined. So the overall, there is a daily total traffic for a root server letter. This I said it wrong. It's not the instance, but the letter identifier. Yeah, that's it.
Maybe you should
root
take
server
this offline.
identifier.
Yeah.
Yeah, maybe you should take this offline.
Wes?
Hey, William. So first off, thanks for doing this. This is actually sort of the analysis I've been waiting to come up. I've done my own in the past that showed for my house, in fact, the amount of traffic went down. And I think it will be sort of, use case dependent in a lot of times. Also note that I agree with Ralph that the traffic, per source address needs to be accumulated across all the 13 routes, and that's harder to do. V6 resolvers can actually move around, so it may be that you might be double counting some addresses, and that's sort of impossible to figure out at the moment. And V4 can too, but that's less likely. And then improvements will likely bring down the data as well. So the gzip compression that has been mentioned, as well as doing head and SOA queries to test for freshness and stuff like that, should help. With respect to total traffic, I'd be happy to help you and give you some figures straight from BRoot that's actual. We can certainly do that, especially looking at diddle data or something. We can actually get total traffic per address. My guess is that it'll greatly benefit some resolvers, whereas if it's a resolver running on my phone, probably less so. You also have to make sure that cache filling may not catch double queries. One of the changes I put into the documents like yesterday was you really should do NSEC aggressive caching if you're doing cache filling, because without it, you're actually just still leaking all the negative answers, and that doesn't really help. Dwayne also, well, the final point, Dwayne actually talked about misbehaving local root clients. I have one at my ISI local root servers that queries me, does a full AXFR transfer every couple of minutes. I haven't gone back to go contact that person, but I should probably do that.
Okay, thanks.
I'm next to Yao. keep it short. Yeah, we should definitely add something about caching, right? If you do, instead of grabbing the file each time, you do an e-tag, and like the file's the same, don't grab it.
Yeah, definitely.
Just as an interesting thing, if you get it from, and I only discovered this a few days ago, Kim pointed out, the URL that you're currently fetching from,
Yeah.
if you end it in .gz, it turns out there is already a gzip version that
Oh.
Diana has. I don't think that that's like the canonical version. It just
Okay.
happened to be there.
Okay.
And I'm out.
Yeah.
Next is Richard.
Yeah, hey, Richard Varens, well-known DNSSEC hater. I think it's ridiculous to include DNSSEC numbers in this. Like, if the resolvers are fetching these things, there's no need for the DNSSEC because in like 3 or 4 nines of cases, it's the resolver verifying the DNSSEC, and at that point, you might as well just verify the TLS. It is exactly isomorphic in terms of the security properties you get. So I'm like hugely supportive of the effort of moving the root zone out to the edge. I think it's ridiculous that we have servers sitting there with a library service for a couple 100 kilobyte file. We can just sync out. So yeah, absolutely, let's do this. But like, let's sync the stuff that matters and not the stuff that's not giving you any benefit.
Okay.
And last, we have Mr. Jeff.
Jeff Houston, look, far from me to accuse DNS folk of being obsessive compulsive to the worst possible level in the entire IETF zoo, but we are.
Yeah.
And in some ways, this was a really simple thing. We're not actually trying to relieve the load on the root servers. If you ask any root server operator, they would say, we have buckets of capacity. It's not that we're dying anytime in the next, geological eon. That's not the problem.
No.
And the other thing is, it wasn't to try and do it in line. It really wasn't. It was a simple observation that says, if you have the zone signed with Zone MD, if you get it, even from the local garbage truck as it wanders past your recursive resolver, if the signatures validate, you know it's current and authentic.
Yes.
So why bother doing it in the DNS? Our observation was, there's this massive web object distribution industry,
Yeah.
and they serve a few petabytes per second as far as I can tell.
Yes.
They're bloody good at their job and they do a lot of it. You could throw the DNS root zone into that ecosystem and no one would blink for a second.
Yeah.
And so you don't need to try and put it in the DNS. You really don't. It's just a web object.
Yes.
And all you're trying to do is to get the zone back to the recursive resolver. And you probably shouldn't put it in the cache. You should treat it as an authoritative zone that you are also able to serve, in which case you get over the whole thing about cache dynamics, etc. Now, having tried to say it, and people have tried to say this for about the last 10 years, every time it gets said in an RFC, the obsessive compulsives, some of whom are in this room, leap up and say, but you've forgotten this and that and so on. Not really. The answer is really simple. Get a signed object, pull it across, validate the signature, and pull it in as a piece of authoritative data.
Yeah.
And Not's answer is the right thing. We observe it changes once a day. Do it once a day.
Yeah, it's the prime reason why I also like the proposal. To have the DNSSEC signed version of all the glue and all the non-authoritative.
Far
data
be it
as well.
from me to say that Unbound are worse than most in terms of obsessive compulsives. But, doing a fetch every 30 minutes,
Yeah. Well, it's fixed now.
Thank you very much. And thank you for having actual data.
Yeah.
We like data. Alrighty, next we have Wes, who I believe is going to ask to present, and he will share his slides from Tokyo.
The request slide thing, you have to grant, there we go. Okay.
It's still being shared.
I'm making sure that I get the right one. How's that? There we go. Okay, so I presented this a week ago at something at the ICANN meeting, but what we were looking at was Joe Abley had a wonderful draft about what would happen if we make a name server record point to dot for something like dot internal. And so I wanted to see how crazy is that idea. So given that, I did a few things. I did some background on sort of some name, what does this mean, right? Names that do not exist. So I'm going to walk through that. I will explain my experimental test setup, show my results, and then the conclusions that I've drawn from it since then. So first off, the DNS fails in many ways. I think we just talked about some of that. Operators fail to deploy zones properly. There's broken infrastructure, or names that don't exist. And names that don't exist globally happen because corporations especially are really good at creating internal corporations, internal namespaces. The three most common were corp, home, and mail, which still don't really have global allocations for those three because of the conflicts. So SSAC in ICANN space, recommended using .internal. And then ICANN actually made a pledge to not delegate .internal so that it would be the safe thing that would never be assigned to anybody. And we'll come back to that in a minute. But my real question is, well, what happens when you actually query these things? What does the DNS do? So this is actually the board resolution about .internal. The important thing is that it says the board's not going to delegate it in the future. I actually meant to remove those slides, so we'll just go on. So what happens when you want to do something like resolve child.parent? There are three cases, right? The parent cannot exist at all. The parent exists, but the child doesn't exist. Or the parent NS record is broken in some way. And there was actually three examples of that. There can be internal name server records with no glue, so it's a broken internal bailiwick kind of problem. There can be a name server pointing to an external name server record that doesn't exist, or Joe's new idea of a name server pointing to dot. This is not internal specific, but I'm going to talk about internal a lot, and then we'll show my example of testing it outside of internal space. Essentially, the parent that doesn't exist at all is exactly what .internal looks like today, that the TLD does not exist. So let's walk through some examples of what's actually going on here. What would happen if you query for something .internal and you're inside your corporation on the left-hand side, right? The corporation sort of has its own root. It has an internal resolver or whatever that says internal does exist, and you'll get back a record. You'll get an A record. It'll may or may not be signed. It doesn't really matter. And you will remember that as a client for the lifetime of that TTL. So what happens if you query externally? You've taken your machine, you're outside the world, in the real world, and today .internal doesn't exist. So you're going to get back a NSEC record with indicating that the name doesn't exist. It is signed, and you possibly will believe those results for the lifetime of the NSEC record, the TTL of the NSEC record. If, on the other hand, and so these are sort of the three possibilities of what might happen in the real world. And I added this max line yesterday, and really I should have redone the slide, but I'll walk through it. So if .internal was actually an empty zone, which it's not today, you'd get back an NX domain, right? Because you'd actually reach an authoritative server that said that record you're trying to ask about doesn't exist. It may be signed, it may not be. The problem is that you will believe that result for sort of the maximum of either the empty zone SOA's negative caching TTL, which few people remember which ones that is. The name server of the parent TTL will actually remember that. So you'll keep trying to contact that name server because you'll believe that for a while, or the name server of their child TTL. Reminder, this is all what a resolver would do. So everything I'm talking about today is not a stub resolver. It is a recursive resolver, that may be querying from outside. The final one is that if you do a name server query for dot, you'll actually get back a serve fail. And that serve fail is not signed. And the TTL, the length of time that you'll remember a serve fail is on the order of a second or two based on current implementations. All right, so all of that's kind of boring. So why would you think about this in the first place? Because it turns out that resolvers move, right? If you have a resolver on your laptop, somebody pointed out that systemd, resolve D, or whatever it's called, actually does this to some extent. It can move. So they can move from inside to outside and outside to inside. So let's talk about the first case, right? You're inside, you have queried for an A record, you're queried for mail.corp or something like that. You get back an A record and you're going to remember it for the length of the TTL. Well, if you have that in your cache and then you move outside, you will remember that for the lifetime of the cache, right? So you'll actually keep the A record around. You might try and contact your mail server, and that actually won't work because it may not be reachable from the outside. But other than that, it probably won't break you because you're still not going to fail to get to your internal mail server. That's not necessarily a big deal. The reverse case is potentially worse, right? You're outside, you've queried for a, something.internal, mail.internal, you get back a signed NSEC record that says this doesn't exist, that you may believe it for a day. So if you remember this and it's like the records today for .internal doesn't exist, you're going to possibly remember that it doesn't exist for a day. So you move your laptop inside, your corporation, you query for mail.com, and your local resolver says, nope, that doesn't exist, and it's going to refuse to send you there for a day. At which point you'll probably go home at the end of the day and you'll still continue to fail the entire workday. The other possibility is if it was an empty zone, you could actually get a NX domain back, and you'd sort of control the length of the TTL if we sort of decided that something like this should happen in the real world. This is not today. So the problem is that it depends on the negative answer TTL and the SOA record, like I mentioned. It depends on the name server's TTL records, and those are currently 2 days in the root. So this is it could be better if we could actually control the TTLs of the name server records down to something short like 5 minutes, but that would be hard to do at the moment. And then finally, if we actually made .internal be an NSEC record pointing to dot, you'd get back a serve fail. It would be very, very short remembered, and every time you queried it again, you'd end up sending more traffic up to the root to ask for .internal, or if you were running local root, it would be immediate. We'll come back to this in a bit. So the real question is, a lot of people looked at this and went, well, if you have a name server pointing to dot, then you're going to go back to dot and ask for .internal, and then you're going to go back to dot, you're going to ask for .internal, and you end up in a loop, right? So I thought, well, we can test to see if we can break the real world. Let's try and test and break the real world, see if this actually happens. So I created an infrastructure setup using 5,000 write batlist probes, randomly selected. I dedicated 2 domains to doing this, one under .com and one under .games, just wondering if new GTLDs were acting differently. So that's the domains. I'll refer to them as sub-BBB. That's just a unique prefix for doing greps on the PCAP traffic. And they were all done with one authoritative name server, recording all the traffic that happened to that authoritative name server in PCAP so that I could analyze it. Note that with one server, it did mean that you'll get timeouts and things from things really, really far away because it took them a while to build up their cache, but I tried to work around that at least a little bit. So the 6 tests that I did, one is querying for an existing domain that does exist, sort of as a baseline to control. One is querying for a non-existent name, like does not exist internal. One was querying something that doesn't exist, like name.subBBB.frostedx.com. One that was querying for a non-existent subdomain. So that's sort of what .internal looks like today. And then one that was querying for a broken internal bailiwick and broken external bailiwick, and then one finally for a name server pointing to dot. And I wanted to compare them all to see what these were like. So the analysis that I came up with has sort of 3 vantage points. One is from the data that write batlist itself returns. One is for PCAPs from the authoritative server. And then one is traffic received at bgroot that I could safely grep out as definitely mine. So let's start with the write batlist data. This is sort of the different types of answers that we got per test. And this is fairly complex. So there's basically, I repeated the test 6 times, 3 for .com, 3 for .games. And this is really confusing and blurry. So I did merge it into a single slide that makes it a little bit more easy to look at. So in all of the tests for things that exists, we got back mostly no error response in the write batlist data. That's sort of what you would expect, right? There was no error. I could actually give you the data. So that's for something that exists. For names that don't exist, either because the record itself doesn't exist or the subdomain it was in didn't exist, you get back an NX domain. Again, mostly what you would expect. And then finally, for name servers that don't exist, that includes a broken internal bailiwick, a broken external bailiwick, and a name server pointing to dot, you get back serve fail. Again, not super surprising. This is sort of what we would expect. I also put it into a heat map just for comparison, and we'll see this again in a minute, but you can break these down into the same sort of things. The big blue bar at the top left is for names that exist, and you get back no error, and then NX domain and serve fail. Then you do get back a bunch of timeouts at times, but we'll come back to those in a minute as well. Again, the timeouts could be for bad probes. There's a lot of bad probes out there. So from the RIPE Atlas conclusions, my thinking is for results that are expected, exist, doesn't exist, and name server records, we really get back the answers we expected, although there is some weirdness. And most importantly, for an NS record pointing to dot, they're no worse than the other two main failure cases, like a broken external or internal bailiwick, which is rampant in the internet today. That's not saying we should do it. I'm just saying that's sort of, if I'm going to compare it, all the answers, all the results came back looking for, those situations that are already prevalent today. So let's look at the PCAP data. So again, these are PCAPs of all of the traffic received at my authoritative server. And we can actually break this down into bits. So this is hard to look at, but what I want you to see is a few things, right? There's 6 sections that you can see between the red lines, and there's basically 6 peaks in each of the tests, the way I did it, and then 3 of those individual peaks inside. One is for .com and one is for .games. And if we break it down a little bit, the second little tiny peak is, and it's not always little, is what should be cached. So the first peak is the first test. The resolvers definitely haven't seen it before. The second peak is they were queried again like 3 minutes later, the same set of probes. So once I pick 5,000 probes, I use the same probes for all of them. The second peak means it was inside the cache length. So in theory, they should have been able to cache it. The fact that there's a peak at all means that they didn't necessarily cache it. The third peak, in each of the series is for things that were beyond the cache length. So essentially, I queried once, I queried again within the cache length, and then I waited until the cache definitely expired 10 minutes and then queried again. So you can see that in this, there's no massive peaks in any of this, even when you break it down. So I decided, well, let's forget that and let's look at just the top 10 source IP addresses and see, is there any address I actually got on any resolver that just went haywire and was just sending a ton of traffic at some point, right? And as you can see, the top 10 IP addresses really are behaving in a peak, right? There's nothing that's suddenly sending a lot more traffic, that didn't die off immediately. So that's actually good news. It means that even with a name server of dot, I was not looping. Except that last slide, this is from my second run. I actually ran the whole set of experiments multiple times. The second run showed nothing. The third run, on the other hand, when I looked at the top 10 graphs, you can see that there is one address that is not exactly behaving properly, right? It's actually generating traffic longer than expected, right? So everything else dropped off immediately, but then there was one that kept sending requests over and over and over. One thing to note is that you note that address is sending requests for all the broken instances, not just the name server of dot, but it's also sending it, the same requests repeatedly for a broken internal or external bailiwick. So again, it's pretty much the same as, so this is the same thing, but with 3 addresses. Pretty much the same thing as if it was querying any broken infrastructure. So that address, I looked at the resolver of that address. It just happens to be an address in Russia. No harms, no references to the country. That really doesn't matter. A broken thing could appear anywhere, but that's the ASN that it was coming from. If you look at the top 10 ASs, you'll see that it's not terribly surprising that infrastructure that has a lot of public resolvers or a lot of infrastructure that a RIPE Atlas node could be sitting in happens to be also sending the most traffic. Cloudflare being an example, or Google, or things like that, they're going to send the most because they're going to get queries from a lot of different places around the planet. So then finally, I looked at broot data. So this is the checks, the requests seen arriving for something under sub-bbb.frostedx.com or .games, arriving at broot. You know, nothing huge. If you look at the queries per minute on the left, that's, you know, 150, something like that. The previous graphs were on the order of thousands per minute. So not a huge amount of traffic seen at the root. The point being is that, you know, I wanted to see, is anything hammering a root server because it was caught in a loop, and I could not find evidence of that, at least from one root server. Obviously, I can't check them all. Even top talkers showed, you know, nothing unusual in that particular case. And so what conclusions can we draw from all this? So conclusion number one, all error conditions cause more traffic. You'll note that the good ones on the left, for a name that actually does exist, all the peaks are significantly smaller than all the peaks on the right, where it doesn't matter if the name didn't exist or if it didn't exist because it was a broken name server, they all cause more traffic. Two, broken DNS, broken authoritative DNS is the worst. Serve fails aren't cached, as Mark Andrews wisely pointed out on the mailing list. Serve fails, because they're not cached, that will actually repeat every couple of seconds because current resolvers don't cache that. I will note that in Joe Abley's document suggesting in a name server point to dot could actually be a signal that this is a name that didn't exist, and in theory you could cache it longer, but that there's nothing that implements that code to date. Conclusion number three, a name server to dot is actually no worse than the others, because those bad NS records for broken internal or external ballywicks are also going to cause serve fails and also act in the exact same way. So an NS to dot actually is no worse than the other really badly broken stuff out there. That does not saying we should do it. I'm just reporting results. Conclusion number four, there's really not much of a difference between COM and games. I sort of expected that, but you know, I set it up to test two top-level domains of different historical lengths. It's a good thing that it seems like the world seems fine with COM and games being fairly similar. Conclusion number five, an empty zone is the best when you can control the data, right? Can you control the name server record TTL? Can you control the NX domain TTL? That's probably the best, because you can actually control the length of time that a resolver might cache that negative answer. NS equals a dot may actually be better in cases where the name server length is a day or 2 days and you really can't control that, which is still going to put you in a broken state when you wander, you know, from an external entity into your corporation, for example. Conclusion number seven, strange things always exist. They always have on the internet. This surprises 0 people at this point. They're kind of hard to track down. Stranger things always exist. Can somebody explain to me why I was getting up of 20 no errors for things that didn't exist, or name servers pointing to dot, or broken name servers? I would not think I should get no errors as an answer, as the R code answer, but I did, a lot of them. Conclusion number 9, even stranger things are afoot at the Circle K. I got 22 queries for quad A, for A6 records, which is the earliest A6, you know, quad A like record for IPv6 that I think was deprecated 15 years ago, I forget. I got 4 queries for CNAME. So there are 4 resolvers out there that weren't querying for the record with an A record or whatever. They were literally asking, is there a CNAME there? I don't know why. That's for a record that exists. There were a couple of things that were asking for MX and text records. Maybe they wanted to send me mail, so they're saying that my name server is broken. I don't know. So with that, any questions, except for the last 3? You can't ask questions about the weird stuff because I can't answer those. This is actually a picture of a sign that I saw here yesterday. It's just outside the building that we're that the remote offsite is in, and I thought exciting amusement properly summed up the conclusions from all this. Anybody with questions or comments? Yelling at me for the way I did it, incorrect, wrong. No hands? Warren, you need to, you know, create hands. Otherwise, you gave me too much time.
Come on. Wes said it's a perfect opportunity to shout at him. I'm sure somebody would like to shout at Wes.
That's funny because when I gave this talk a week ago, there was a bunch of people that had to come up to me afterwards because there was no time for questions. Now that there's time for questions. So I think, Warren, I will turn it back to you at that point. And Jen didn't yell at me for running over in time either.
We actually are ahead of time.
Okay.
So thank you very much. Next, we have Mr. Peter Thomason, who will talk to us again about DNS stuff. A reminder for everyone, if you all want less DNS topics, you're going to have to offer to present something else because we can only present what people have offered. Here we go. I mean, I personally think DNS is awesome, but some other people incorrectly might disagree.
Hello, hello. All right, Peter Thomason. I'll present some measurements about what happens if you register domain names that are bit-flip variations of the rootservice.net domain, and then see if that causes any resolvers to latch on to use them. The measurement was done in 2 stages, so there's different degrees of interestingness in the results from the first and the second stage. We'll get into all of that. So what's bit flips? So very briefly, you know, memory can suffer random errors in which a bit is corrupted, and that can have various reasons. And it's very unlikely to happen, but it does sometimes happen. And if you have sufficiently much memory, then eventually it'll happen, and maybe it happens in a resolver. So let's see. Here's a bunch of reasons how that could happen. For example, manufacturing, or you operate the hardware outside its intended specification with temperature and all of that. There could be a radio contamination. There's actually a case of radio contaminated packaging that caused the memory to actually fail. And yeah, so some people think it's mainly to cosmic rays. I don't know if that is true, because of the results that we later see. They don't look like it's random bits flipping. So it sometimes seems to be structural defects in memory. Anyway, the common assumption that hardware operates correctly is usually the case, but it's not always fulfilled. And then, yeah, things can happen. What's interesting is that when that happens, you don't need to do any actual hacking. You just need to exploit the fact that the machine is doing something wrong. And what exactly then goes wrong in the application, or maybe in a middle box or something else, that impacts what you can do with that from an attack perspective. In general, when you consider the 3 security properties, confidentiality, integrity, and availability, here the integrity is affected, and that can, of course, sometimes be exploited to impact confidentiality also when you manage to extract a key, for example, because it's sent to the wrong location because of the integrity failure. Mitigation for that is to detect it using checksums, for example, or to do error correcting codes in memory, but that is not very common, mainly, I guess, because it's rather expensive. I mean, it's not expensive per bit, but if you buy a lot of hardware and it has that feature, then it's a difference. So the whole thing is inspired by Warren's experiment that he presented last year at an ICANN lightning talk. He registered a bunch of names that were bit flip variations of commonly used names like Microsoft.com. One variant of that is Microsound.com. And he stood up some fake systems under that domain and received traffic that then looked like it was meant for some cloud endpoints or something like that. And then depending on where in the connection stack the problem happens, for example, whether it is before or after the browser composes the TLS handshake data, then you might actually succeed, for example, doing a TLS handshake with a fake name, but still getting an HTTP request for the original name. So that allows you to extract cookies and stuff. So that's actually quite interesting. And I thought maybe, you know, if we do the same thing for the root servers.net, that would be interesting to see what happens. So, okay. One quick reminder. So there's something that's called priming queries. Resolvers have their bootstrapping configuration about what the root server host names and their IP addresses are from what's called the hints file that is usually hard-coded. And every once in a while, the content of that might change, or maybe it doesn't change, and the maybe the file doesn't change, but the root server's IP addresses actually get renumbered or something. In that case, a resolver can do what's called a priming query and update its knowledge to be able to use the new name servers. And that is a situation where the root servers.net domain names actually get queried. And that's where these bit flips could could potentially be exploitable. But I don't know how many priming queries, for example, happen in practice. And again, a condition of that would be that the resolver has undergone a bit flip before that. Yeah, so we talked about this. So here's what the priming query looks like. So this is essentially a reminder. It's just an NS query for the root name. And what you get is the name server records for the root, which is a to m.rootservers.net, and also the glue for that. And essentially that looks like the hints file content, which is pasted here as an example, just with different TTLs, interestingly. Excuse me. All right. So, well, that just said, previous slide, when you don't use DNSSEC, then you won't be able to detect such a spoofing. All right, so we registered wootservers.net, which is the name server infrastructure that hosts the zones for the fake rootservers.net zones, right? So for example, if you have a.rootservers.net, but you replace the R by a S, for example, which is a bit flip, then the suitservers.net zone has to be hosted somewhere so that you can then later point to the fake root servers. The name servers on which those bitflip variations of rootservers.net are hosted is wootservers.net, okay? So that's why it's called the wootservers experiment. The setup is, okay, sorry. So what we did is that we registered all the 1-bit flip variants of rootservers.net that we could actually get a hold of. Total there's 56, and 8 of those were already taken. For example, bootservers.net. So I don't think that is necessarily an attack. It's a plausible name to have. And the other 48 that we could get, we registered. It originally was 47, and then one of the others got available. Oh, thank you for the water. Might be preferring coffee. Much appreciated, thank you. And yeah, what's interesting is that there's more variations actually where the bit is cleared as opposed to where the bit is set. That's because either lower or uppercase numbers, I don't know, I don't remember. When you flip a bit, they might also correspond to a digit. And in the other way, that's not true. And that is, this opportunity is always in the same direction where you have to clear a bit. So that is why there's more clearing opportunities than setting, which I found interesting originally. I found that confusing. So the name servers of that are, as I said, a and b.rootservers.net, and we recorded traffic on that. We also recorded traffic on the actual fake root name servers that we set up under a to m. And then the bitflip variant. And Rutgers University, which is my alma mater, was nice enough to allow me to store data and use their CPUs to do the analysis. So this was done last year, July, until mid-January this year. There were 16 gigabytes of data at the root servers name servers and 220 gigabytes of data that arrived on the fake root server infrastructure. And of course, as usually, there is a lot of like random noise, so needed some sanitization. Let's first look at the traffic that arrived on the root servers infrastructure. So A and quad A queries for a to m dot a bitflip variant of rootservers.net. So those were on 2 VMs. They have different IP4 and IPv6 addresses. So that's A and B. And here's daily queries for the A name server for any single letter from A to M dot any bitflip variant of the rootservers.net domain. Actually, the .NET TLD doesn't have a delegated bitflip variant, so that's we didn't try other TLDs. And you can see that there is a constant influx of queries of a few hundred for IPv6 queries and a few thousand for IPv4 queries. So it looks like these names are actually being looked for. The same happened on the B name server, so these look pretty much the same. Looking at number of query sources, that is also not unexpected. There was a variety of query sources, v4 and v6 sources. Same for the B name server. What's interesting is the frequency of bitflip variants. So this is both name servers together. And I just plotted from the 48 names that we registered, which are the most queried ones. So typically, in the test period, all of these variations got around 34,000 queries. And for some reason, rcotservers.net stood out. Later, there will be some hints on why that is. So if you consider on the right-hand side, the O to K flip is in the third bit on the right. And the second winner was rootservers.net, where the last E in the second label is replaced by a U. And if you look at the thing on the right, you can see that that is a different bit that is flipping here. And for the other names, things didn't really stand out that much. For some reason, the very first name in the list, the root server rr.net, is an outlier towards low numbers. It only had around 2,200 queries. I have no idea why that is. What's also interesting is that you can get double bit flips. So there were 3 instances of rcode servers.net, which seems quite unlikely to happen, and actually the number was pretty small. I don't know by heart which bit in the ASCII table takes you from V to R. So I don't know if that's also the third one. I don't know if it's the same bit flip, so to speak. But anyway, it is also 1, 2, 3. Yeah, it's I think 7 bytes apart. So it doesn't seem to be like a hardware layout thing. I don't know, whatever. So this is for A queries. For quad A queries, you have the same winner, but there is a different, there's a different second winner. So I'm flicking back and forth. I don't know why that is. So the second winner now has a bit flipping from R to S. And you can see that on the on the right-hand side. That's the first bit. And overall, there's less quad A queries. So far, so good. All right, this is the frequencies of other, or actually all prefixes that I saw queries for. We actually only answered for A to M, and the rest was not answered. Still, we saw queries for things that were like random. So there's a bunch of wildcard queries, A and quad A. So if you look at the bottom right, there's about 2 million of them, which is much more than for all the other names. And yeah, so for the other letters and numbers, with some distribution, I don't really have an interpretation for that. Maybe some of that is bit flips of the actual single letters or something. Okay, so the second step is to look at the fake root server infrastructure. So those are the servers to which the A and quad A records we just talked about would be pointing to. So we observed 146 million queries in those 6 months that we did the measurement. 75% of those were any queries for names like europa.eu or esc5.net, and for .sl. I don't know why .sl is such a common name for any queries, but I think I've seen that in the DNS org chat reported by other people too. And around 24.6% were TXT queries for names like cisco.com and a few others. And if you actually look at the TXT responses for those, then you will find that they are really large, several kilobytes, and the same would be expected for a reasonably engineered any query. So maybe all of these queries are just amplification attacks. I'm not an experienced resolver, a data analysis person, but I would think it looks like that. So if you remove all that, which sums up to 99.9% actually, then around 60,000 queries remain, and so those are the interesting ones. I also removed other queries that didn't make sense, like from the chaos class. And yeah, so it's hard to say what that means, because if a real resolver would latch on to that stuff, you might expect more queries, or maybe not, because the referrals are all cached. Yeah, so some refinements might be needed to tell exactly what that means. I'd like to emphasize that we did not spoof any responses. So those fake servers actually were DNS disk proxies to the K root server. And so if anyone ended up using that stuff, it would still work in practice for them. All right, so from this first measurement phase, the half year, here's some interesting queries from a European mobile ISP. So they're all from the same /16 subnet, and they stretch from July to October. The first name at the top, geolocation.garmin.com, something Cloudflare. Garmin is a manufacturer of car navigation software. So this is on July 11. Then on July 26, there is a query for something in Volvo Cars cloud endpoint, it looks like. And in September, something vehicle thing too at Amazon. Interestingly, this name has, the Q name has 2 bit flips in it. So the whole thing, including the new line, is a long Q name. And I think it should both times be EU-West-1A. I think that's what the name of the cloud endpoint should be. And in one case, the dash is replaced by a closing parenthesis, which is a bit flip, and the S is replaced by a W. So this is actually something seen rather frequently in the subnet, that there's multiple bit flips in this sort of query name. Then also the Amazon AWS domain is hosted at Amazon name servers. So there were also queries to the to resolve the name servers host names. For example, these ones here in October. And not only did the question end up on our infrastructure, which requires a bit flip, it also had a bit flip in the co.uk name, which actually it asked twice. So once with and once without the bit flip. I'm showing you this to exemplify that the problem in this subnet is apparently a permanent one, and apparently it's related to car stuff. I don't know why that is, but maybe there is, for example, so I said this is a mobile ISP, so it's possible that there is a car that has a SIM card, and every time the car starts up, it'll do these queries or something, and then the memory within that system has a manufacturing fault or something. I don't know. I find it interesting, though, that this car apparently is doing the resolution itself. I would expect it to use some resolver that is not within the car. So I don't know. And then the question wouldn't be coming from the mobile ISP, right, if it was the resolver. Okay. All right. Next improvements. I looked at the stuff that I just showed you first in mid-January, and then based on that implemented some improvements. And those measurements were run for 3 weeks, February 5 till 27. So this is not very much time. So I'm considering to keep this running for longer. It comes with some cost. I mean, the domains cost a few $100s per year, and then you need 4 VMs. We've talked about 2, but you will see there's 2 more now, and all the storage. So if anyone is collaborating on providing, or is interested in collaborating for providing these resources, that would be pretty cool. But I'll tell you about the improvements first. So I said earlier that we had only answered, I made a mistake earlier. I claimed that we only answered A and quad A queries for, no, I didn't make a mistake. Anyway, so for the, okay, sorry. What's written on this slide is not correct. I said earlier that for a.m.rootservers.net, we did send a response, and then if there was a question for q.rootservers.net bitflip variation, we did not send a response. Now we changed that. We made those bitflip zones real zones, so that we would send NX domains for the single letter subdomains that don't exist, and that we would also not drop and instead respond to NS and DNS key queries for those fake root server names. So the bullet here is wrong. It should be saying, do not drop NS and DNS key queries for a2m.bitflip of rootservers.net. The names that are listed here are just regular zones, so they never dropped anything anyway. So it's just a typo here. All right, so we made these real zones. Then we also changed the responses that we would send for the fake root server names, such that we not only returned the A or quad A record for the fake single letter root server name, we also included an answer for the non-fake name. And then depending on where the bit flip happened, when the client made the query, it might be expecting the wrong or the correct name, right? Because it might be preparing a question for the real name and expecting the answer for that, and the bit flip happens later, in which case it'll be useful to have that second response in the second answer in the response. To make sure that these cases are distinguishable, we returned different IP addresses for that case. So those are the new VMs that I mentioned, p and o.rootservers.net, but those names don't appear anywhere. And the same thing for IPv6. All right. We also found in the data that we repeatedly saw priming queries, and we discussed before that that could be interesting. So we actually started tailoring the priming response. So all other responses from the fake root infrastructure were actually from the K root and DNS dist proxied. And only for the priming responses, we did return our own name servers. So this is where the ONP servers appear, and we did return their IP addresses in the additional section as glue, but those are different IP addresses from what you would get when you query the A records for the single letters. So we can distinguish whether the traffic we get is from a single letter address query or whether it is from a priming query, okay? And yeah, so this is 2 name servers here because diversity and all of that. And then actually, yeah, so 2 are required because of diversity, and then the IP address is shown here, and on the previous slide, actually share those VMs. So each VM has 2 IPv4 and 4.6 addresses, and then you can tell by the destination address and the PCAPs what's happening. All right, so some interesting queries after improvements. There's the Ford Transportation Mobility Cloud, which, I mean, just went to autonomic.ai, which is apparently a thing that Ford is using. I'm spelling out the name here because Ford is just the user of it. It's not Ford's infrastructure that is wrong. The IP addresses here shown for the sources are not from Ford. They are from an American mobile provider. So the problem seems to be similar to the one that I mentioned earlier with Volvo cars, except that now it is American and not a European provider. What's interesting here that priming queries are shown, and then the red IP addresses show up here, which are the ones that you get when you look at the glue from the priming response. So this looks like whatever was doing this resolution thing did actually do a priming response and later send queries to that, which is interesting. I also don't know why the queries are being repeated so many times within a few seconds. So this is all on February 17, within a few minutes from the same source. And those are not serve fails, right? Because we did give the proper referral for the .ai TLD. And yeah, so maybe something else is broken on their part. All right, so here you can see, again, Volvo queries, also American this time. The stuff is related to a product that's called a Gbook, which is also a navigation system, I think, from Japan. And it has been discontinued, I think, like 10 years ago. But yeah, so maybe that's the obsolescence time for memory stability or something, I don't know. Anyway, so you can see also that the bit flips here sometimes happen in the queue name. For example, .com gets turned into .aom. It's actually sort of reasonable that maybe a requery is happening here. And also the name that is being queried here is a C name for something cloudfront.net. And I'm not pasting all the queries here, but there is a whole lot of cloudfront.net queries, including cloud.dront, which is a bit flip of CloudFront, and various other combinations of that stuff. Here's the Gbook queries that I mentioned before. Those also happened to the IP addresses that you get from the priming response. The previous queries were from the ones that you get when you do the single letter lookup. So I don't know what's what. It's the same source address asking the questions. And that subnet also did ask a question for voltocars.com, and the endpoint that is here in the subdomain is actually the same one as earlier in July in Europe. And so that seems to be the same system. Note that it's a few hours apart from the Gbook queries. Not only hours, it's actually a few days. And now if you look at volvocars.com, not Volto, then you will see that the name server for that is cscdns.net, and the name server for that is cscudns.org. And yeah, so we see queries for addresses of both these types of name servers that follow when you do the resolution for volvocars.com, ending up on our non-priming response IP addresses. So this seems to be a resolution cascade that uses all kinds of things for some reason, and apparently it's multiple resolvers in that network because the source addresses are different, or at least you know, multiple IP addresses on the same interface. So this looks like a real resolution cascade to me, and again, it seems to be in the car context. We couldn't observe many non-car things. So to sum up, there were about 10 million queries seen for the single letter names and 100,000 1,000 queries on the fake root name servers after pruning. And we found around 10 interesting resolution cascades within the last 3 weeks where we did this measurement with the improvements. We didn't send any fake referrals. If we did that, then maybe we would see, like maybe the resolvers don't come back to us because they've cached whatever the .com delegation. And then, yeah, they ask the .com name server, and we don't know if they actually ended up there through our response or whether our fake infrastructure is not of any relevance. So we were quite hesitant to actually fake any referrals, which is why we don't know that. But it's possible that if we did that, that actually some resolver populations would latch on. I don't know. And I also don't know for how long they would do that. I guess until they reboot or something, I don't know. Anyway, so this could be refined by looking at country origins and ASs and whether the sources are resolvers in the sense that when you send a query to the source IP address, whether you can use it for resolution. I've tried that. I'm not sure whether with all, but at least significantly many, and I did not get a DNS response from any of the sources. On the other hand, the source IP addresses from resolvers are not usually also serving DNS, so I don't know. And then I haven't looked into any DNS aspects of it. Yeah, so that's the state of things, and I don't know how interesting that is. The problem is certainly mitigated in the sense that regardless of what we measure or whether that continues, the names are now taken. So if there is any risk that cannot currently be exploited because we don't do any bad stuff with that, should we keep these names registered? Should we keep measuring? I don't know. So thank you.
And for some reason, the slide share suddenly stopped, but Dwayne is up.
That's fine. This was the last slide anyway.
Yeah.
Hi, Dwayne Wessels from VeriSign. Thanks, Peter. This was really interesting, of course, and very clever to use different IP addresses for priming and single address queries. I kind of expected to see maybe some data on which one of those two was more commonly referenced later on. I don't know if I missed that, or maybe you just didn't have enough data to do that.
Yeah, I haven't extracted that number, so
Okay.
we can, it's hackathon time, so.
Okay, cool.
Yeah.
Thanks.
Some other question?
We have a Lorenzo in the queue, who I believe is remote.
So the second one.
Okay, so let's see if this works. Hello. So I'm sort of wondering how you can get all of these bit flips. It seems to me that if memory on the client device was at fault, you would basically see these things crash shortly afterwards with sort of illegal instruction, right? And I'm sort of wondering, do you have any idea about how many of these bit flips come from the client memory, and like, could they be just be induced by the network itself, right? Because that seems for, I guess you'd see checksum errors in that case. Any thoughts on that?
Yeah, good point. So I was thinking if the client is really so faulty with its memory that it has multiple bit flips appearing a few bytes apart in queue names and stuff like that, then probably nothing works on that device. Good question. I don't have the answer. I have not tried reaching out to any of the operators of the source networks. If one was in touch, then perhaps one could look into the actual devices. Maybe the devices, in fact, do crash all the time, and that's why they send so many repeated queries, because they reboot. I don't know. So that was the first part. Second part of your question, I don't remember exactly.
From the network.
Oh yeah. I don't think that it is transmission errors, because in that case, the response would not be useful to the querier, and corresponding follow-up queries in the resolution cascade wouldn't appear.
You did try to answer both the original and bit flip responses, though, didn't you? So technically, if the query had made it to you with a bit flip on the network, you would have answered the original name. That would have gone back. The only failure would have been if there was a checksum failure, let's say in the UDP checksum, and then your server would have dropped that. So I guess you wouldn't have found that because your server would have dropped it due to bad UDP checksum. But that might be worth, might be worth building a server that doesn't care about UDP checksums and answers anyway. Wonder what you'd see then.
Yeah, good idea. I don't have a prediction what would happen. One last thought. So many of the names I showed you earlier, like from the different bit flips, even from after the improvements, even from within the US, those also showed that usually the same bit flips. I think it was the third bit from the back at the European provider and the fifth at the American one or something. I think definitely it looks like a structural thing in the device. Not a random thing and also not a transmission thing to me. But yeah.
Thank you.
Somebody else just had walked up to the mic here and then disappeared. So, there, okay.
It was me, Marco Davids. I think Lorenzo already touched on my question, but I'm willing to repeat it, just from my understanding, because very interesting presentation. I'm not sure if I fully understand it. So my question was, the bit flipped query comes in your authoritative name service. You respond, and you copy the original query in the response, including the bit flipped version, and not the one that the resolver was actually asking for, right? That's correct, right? And have you looked into how resolvers respond to that copied answer in their query, which is not what they were actually looking for?
So we respond as if the queue name that we received is the one that is actually the one that the querier wants to know.
Aha, okay.
Yeah. So,
all right, so that answers the question.
Yes.
Yeah.
And it's true that perhaps such responses in some cases where the resolver is waiting for the actual name and not the flip name will then discard the response. And in that case, it would help if we did fix the bit flip in the copying of the question section into the response. We did not try that.
All right, okay, thank you.
Davison from Alibaba Cloud, and thank you for the sharing, and I think very interesting. But I have a question: is that I think it's true that some of the primary query were hijacked to the bit flipping domains, but how can you tell the difference? Tell the difference between the hijacked bit flipping domain and the real query names, because there are always some scanning the random domains in the internet, and how you tell the difference.
Yeah, that is true. So there was a lot of scanning, like Shodan and internetmeasurements.com and whatever universities. So I actually went over like a categorized queries by source network. Then I looked at who owns the source networks, and I discovered things that were obviously from measurements. And the things that I showed here as the interesting queries are queries that had no indication of being from a measurement from somebody else. And that also looked like actual resolution cascades because they have multiple things after each other that, relate to something the root would first see, and then, a later query for a subsequent resolution of the name server host name for the SLD or something. So these look like plausible things that would usually not appear in a internet-wide random measurement. And one last comment, I think earlier Lorenzo said that he's surprised there's so many of these bit flips. I actually don't think it is very many. I mean, it's a significant number, but the fact that we saw around 10 interesting cascades in 3 weeks, given this is a global thing, I don't think is a very high number. Okay.
Thank you very much. And now, shockingly, we have a talk about DNS. Might actually be more about V6, but a reminder again, if you all want talks about something other than DNS, please propose talks about something other than DNS. Or not, I'm perfectly happy with all DNS all the time. Do you want to use the clicker?
I guess I can use the clicker. My voice hangs out. I'm Jeff Houston. I work with APNIC Labs. This is more a measurement talk than it is a V6 talk. V6 is kind of marginal in this subject material. And it's also about the DNS. Willem's talk was actually a really good illustration of the opposite, and also actually Wes Hardiker's talk. Because when you're trying to measure DNS behaviors, one way is to actually create a microcosm of the DNS environment. Set up a recursive resolver, send sort of queries through Atlas probes and so on, and look at what you get back and generalize it out. And that was a classic example there. If you sort of said, well, I saw these, and then I extrapolate further out to the total load of the root name servers. And there's nothing wrong with that approach, but there's a big leap of faith that what I see in the microcosm is what you see in the entire environment. We in APNIC have been doing almost the opposite, where by using ad-based measurements, we actually seed the entire internet with, I think it's about 45 million ads a day these days. It's a lot of samples. And everyone basically who sits on their mobiles or gets an annoying Google ad, statistically, one time or another, you will see our ad. The ads kind of penetrate across huge amounts of the network. And over time, and we've been doing this for about 15 odd years, you get a big picture of the network. But in some ways, that picture can be as misleading as the microcosm. And the story that I actually want to tell about this is actually a story about IPv6 as transport for the DNS. So to wind this back, and it's winding it back 22 years. Christ, we're getting old. This was an RFC from Alain Durand when he was at Comcast, and I've forgotten who the co-author was. They could even be in this room, so I'm sorry if you are. And it was a sort of a weird RFC. It's ostensibly about V6 transport, and the text said, don't stop using V4. It really was just a reminder to say, too much of the internet relies on V4. You'd be stupid if you tried to do this V6 only. And, the guideline was every DNS zone should be served by at least one V4 reachable name server. Now, this got revived, I think about 4 or 5 years ago, where why aren't we using V6 in the DNS? And there was a long argument at the time about to what extent does V6 make a really bad hash of big payloads. Part of the issues with V6 is you can't do fragmentation on the fly in V6. You've actually got to send back the ICMP message to the host, and the host has then got to resend that packet appropriately fragmented. In TCP, that sentence makes a huge amount of sense because I keep a hold of what I sent, and when I get back that ICMP, I can do that. In UDP, what I just said was bullshit. Because in UDP, when I've sent the packet, it's all over. And I get back an ICMP going, that was a dud. And I go, well, yeah, it probably was. You should resend it. No, I can't. It's gone. And there was this sort of argument at the time, and I certainly had measurements to sort of show that large packet behavior in DNS over V6 was kind of not good. And if you're trying to recommend, as this document is trying to recommend, that we should have V6 for the DNS everywhere, the caveat is that you're going to get jammed into some nasty corners if you apply large responses, for example, Gs, DNSSEC with really big keys. So it sort of was an interesting kind of question. Can we show some data about this? And at the time I was doing data, I'm clicking forward, Warren.
No, nothing working?
Yeah, go forward, please. You've got a problem too. Yeah.
How do I
I don't know.
I might need to stop sharing and reshare.
Stop sharing and reshare.
There we go.
Right. So the assumption behind that more recent document was, why are you not using V6, oh DNS people? It's efficient, it's well understood, it's mature, go and use it. Next slide.
Should be working.
The real question is that true? So I'm not even looking at the corner cases. What I'm trying to do is actually really quite vanilla. Here's a response. It's well under 1500 octets. It's well under 1280. It's not going to run into any of the V6 complications with large payloads. And the question is really simple. If my authoritative name server only answered in V6, What proportion of the entire internet can't see me? Reasonable question. It kind of is testing the maturity of V6 in the broader spectrum. Seems like a decent question to ask, but the measurement is kind of the topic of this talk, because measuring that is not as straightforward as it might sound. Now, what's a resolver? Oh, shit. Because it could be a single platform. I run a resolver. Google run a resolver behind all 8s. No, they don't. They run a large number of machines behind that single service address. And if you go to any individual site, you'll find a large cluster of individual DNS engines behind that. Is it a bunch of DNS engines, or is it a bunch of query engines with a common brain? In a server farm, how do they talk to each other? Do they multicast cache? What is a resolver is actually a really fascinating question in the DNS. And quite frankly, there is no single answer. When you start sort of poking into the DNS, what you actually find is some remarkably aberrant behaviors. And resolvers are not kind of commonly understood as a concept. So when I talk about, well, how many resolvers can reach, an authoritative name server of over V6? Well, I don't know what a resolver is. I really don't. So it's kind of a dud question. The other issue is, if I'm just doing a head count of resolvers, I run a resolver at home, it has me as a customer. Its weighting is 1 out of, how many people are on the planet today? 8 billion? It's teeny. Whereas if I'm running Google, I probably have around a 10% market share of the internet user population, maybe 15%. So I'm talking about the Google resolver as a single entity. I'm talking a massive, truly massive footprint. So just counting resolvers and going X% of resolvers can and X% can't, kind of bullshit, isn't it? It has absolutely no proportion to the experience you and I have as users. So what is a resolver is a really hard question. And I'm not even sure that measurements of resolver behavior should refer to the resolvers. Because like I said, some resolvers are important, some like mine are astronomically unimportant. And then you go, well, okay, what I'm going to test is a query over V6. So what's a query? You kind of go, hang on. A query is simple. I have a DNS system somewhere that's running the DNS protocol. It sends out a packet over UDP port 53. It has a certain formatting. That makes it a DNS query, yes? And if I'm looking at a resolver inside your machine that you're staring at right now, you might well emit one query. But that will go to the local thing that grabs the DNS. And that thing, which is also a resolver of some sort, might well try to fan it out. And what we actually find is that as queries enter into the cloud of the DNS resolution environment, they often get duplicated, triplicated. They often get copied all over the place. Sometimes it's immediate. Sometimes they wait. Sometimes that wait is very, very small, 10 milliseconds. Other times it's more generous, 1/3 of a second. Other times it's Microsoft. They reckon you're a very patient user and they'll wait a whole second before duplicating the query. It's UDP. You never know when the answer will come back. And so the common behavior is twiddle your fingers for a while and whatever you think is a good time, send the query again until A, you get bored, or B, the user goes away or something. Hang on a second. The DNS does not have an interrupt. So when the application says to the DNS, resolve this name, the application can hang in the next microsecond and disappear. The DNS doesn't know that. It's been given a task down at the stub resolver level that then forwards to the recursive and forwards on. It never gives up. Now, some resolver implementations do give up after a timeout. Look, I've been working at this for too long. In Bind's case, it's 7 seconds. In Unbound's case, I think it's a geological eternity, or it could be 2. It just never stops. It exponentially backs off. But as far as I can see, even a year later, I've still got this unresolved query. reboot the machine if you want to kill that crap. The other thing about DNS is that if I refer a query to you and you go, oh, look, I'd like to help you, but I can't, but I think I know someone who can, you forward it on, and you forward it on, and you forward it on. There's no hop count. Unlike IP packets, there's none. There's no trace. So I can set up a forwarding loop and the DNS goes, not a problem, dude. And there probably are DNS queries circling around forever because there's no way of stopping them. So a query is not simple. They have a life of their own. This is just a snapshot of one day in the ad system. And what you actually find is that to resolve a name these days, most folk in red ask for an A record because there's more V4 than V6 even today. The other thing is, of course, these days that the Apple infrastructure, and not Android, but the Apple infrastructure, have taken to the HTTPS query like a duck to water. And these days, almost the first thing it asks for is HTTPS. What protocol should I use for the resultant, fetch? So HTTPS figures, that's the light blue, and the green is V6, A records. So that's the number of single queries that I see for that name. But hang on. Sometimes a query happens twice, 3 times, 4 times, 5 times. I arbitrarily cut that off at 10. I could have gone to around 2,000. Sometimes the queries just duplicate. And the other thing you find is that in a sort of a cumulative distribution, around 70% of queries happen once, but 30% happen at least twice, or 3 times, or 4 times, and so on. It just goes on and on and on. So in trying to understand the DNS, you've got to try and understand root cause, and the DNS is a massive feedback amplification system that's as noisy as shit. And trying to get the signal out of that feedback amplification system is kind of interesting. So I mentioned that the way we measure is to seed the world with ads. No, we didn't invent ads. Google did. Google it's about $1 billion a year, isn't it? If you look at their annual reports, it's what drives the world, or at least their particular part of the world. We just piggyback on. The ads are simple. If you get the ad, it runs the code. You can't stop it. It's on impression, do this. What does it do? It just fetches a bunch of URLs, typically around 10, and then it stops. It's quite silent. It runs in the background. But the thing is, all those URLs have unique DNS names for that instance. So every single ad has a different set of DNS names, and the only authoritative servers out there are ones we run. So we get this remote view of the user. And we get 40 odd million of them every day. So back to that measurement question that I was asking. How much V6 is out there? And the way I'd like to phrase an answer is not, well, 20 resolvers, 1,000 resolvers. No. I'd like to phrase it as users. And I'd like to say, well, if we're sampling users, well, maybe I can talk about the percent of users. So here's an answer. That's, I can't see the slide from here, 66%, 67%? Whatever.
65, 66.
2/3 of the world's users can actually resolve a name if the authoritative server will only answer in the DNS. Cool. How do I do that? Well, I can't see if you successfully resolved in the DNS. I can see your query, but I don't know if you got the query, you got the answer. A lot of problems we had with V6, as you might recall back in the early days, was that you could certainly send the packets out. It was the incoming filters that blocked you. So over there, if I'm measuring your V6 traffic as single packets, I was seeing a huge amount, but none of them were getting back to you. So the web session says, you got the answer and you fetched a web object. And you fetched a web object. So what I'm actually measuring is 2 things. I'm actually saying, well, you could resolve it using V6 only, big tick, and you fetch the web object. Over what protocol? I don't care. So the object is dual stacked. I don't care what protocol, whether you use V4 or V6 to get the web object. If you went and fetched the web object, you successfully received the DNS answer. Cool. So that sort of 60-odd% looks good, right? Obviously, I wouldn't be asking if there weren't some doubts about this. Because when you're measuring, a lot of the time you're measuring what doesn't happen. For 30% of the world's users, they couldn't do the fetch. And that wasn't a positive signal, it was the lack of a signal, right? So why didn't they fetch it? Well, it could be because they didn't get a DNS answer. I can't tell. I haven't got any other code on that user's device that they've seen the ad. It could be that they just went somewhere else because, you know, users are remarkably fickle. They move on. We all do. So they may not have actually hung around and done the web fetch. So what if it's being filtered by middleware? What if there are other factors? Why don't I get rid of the web? Can I make a DNS test that says in the DNS whether you actually received an answer? Yes, you can, because of a strange quirk of delegation. You see, when you delegate a zone in the DNS, you do not specify its IP address. You specify its name. If you want to know why, Christ, ask Paul Vixie or someone who bloody knows. I don't have a clue. It does seem like a weird thing, but the DNS is sort of part of this obsessive compulsive. You can only give names for delegated name servers. Meh. Normally, when I operate a zone and I have a delegation, I'm also a helpful chap. So are you. Normally, you would put the IP addresses inside the zone as well as glue. Whether it's part of the zone or not, doesn't matter. And the referral answer you get has, this is the name of the name service, and by the way, here's their IP address. But it's perfectly legal not to give them that help. No, sorry, here's the name of the name service, go fish. Have fun. So I do. I set up a second zone, which is actually the name of the name server. And the poor old recursive resolver has to stop what it's doing and start to resolve the name server name. And this is where I put in the v6 only bit. Because what the sibling zone then does is say, well, here's the address of the name server you were after, but it itself only answers in 6. What that means is that that third query only happens if you got back an answer. So if I look for those third queries, I know that you could make and receive a DNS query in v6 only, which seems a lot tighter, a lot tighter. So, you know, does it make a difference? Oddly enough, yes. And this is kind of intuitively sort of interesting. Around 15% of users will actually show that they can do v6 in the DNS, even though they didn't get the web object. You kind of go, well, the web signal's kind of lossy. This is sort of intuitively obvious, right? Now, this is kind of what we expect. But the problem with this is averages lie like crazy. Algeria, 60, 70% do it on the web. Glueless delegation, nah, Algerian ISPs do not resolve names that don't have glue records. They just don't. V6 or not, I have no idea. Across the world though, North Africa seems to have this common behavior. Libya and Egypt do it too. They just don't resolve names that have glueless delegations. Who would have thought? And if I go the other way, I also find not just 1 or 2% or 10%, but a massive drop that some folk go in the DNS, yes, v6, no problem. That web fetch, I don't like the idea of fetching a 1-by-1 pixel that isn't even flesh toned, I don't like that. I'm not going to do that. And so a number of countries, Bolivia, I don't know, you can read as well as I can, Myanmar. Myanmar is interesting. Myanmar is a mess to measure Myanmar. It's totally dominated by spam factories in the north of the country. And wow, the DNS gives a decent signal, the web signal is horribly confused. So you kind of think that there's this pattern. What you actually find is massive divergence in both ways. And I can plot that and show, yes, there is massive divergence in both ways. And I can sort of point out that there's anomalies in both directions where DNS glueless is blocked or the web fetch is blocked. So the averages kind of lie. And what I would expect, yeah, about a 10, 15% difference, actually doesn't quite work out for everyone. So then I start to combine them and say, well, okay, in this ad, I'm doing 2 measurements. If you do one or the other, let's going to give you a tick. Wow. As soon as I do that, I get a number that's higher than either. That there's a number of folk who can do a positive answer in the web, but can't do the DNS glueless, and vice versa. And so the actual end result of folk who can do resolution over V6 is oddly enough higher by around 2% in total, which is not what I expected. So what can you learn from this? The DNS is completely balked. Simple models don't work anymore. We are so used to people futzing with the DNS in every possible way. Many national regimes have their lists of names that will not resolve, but bizarrely, many regimes then impose a technology solution which is theirs and, you know, not anywhere else. And so what you actually find as you look across the broad landscape of the DNS is there's no uniform model anymore. There's no stub resolver, recursive resolver, authoritative, life is simple. You actually find it's horrendously complicated. 40% of users in Algeria have their queries come at me from Google. From Google. Does Google do glueless delegation? Of course it does. So something is happening deeper in Algeria that says, I'm not even going to pass the question on to Google. It's just not a question I'm prepared to answer, and refer onwards to Google. Maybe Google is being used to mask the fact that there's other DNS engines actively involved in that country and in other North African countries to do the same thing. So what you actually find is trying to infer the DNS from the observation of behaviors is far more complex than we'd thought. And that simple tests that use a simple model often get misled badly. Yeah, one little thing. Should you use V6 the DNS? I don't care. Go and do it yourself. It's like your problem, not mine. But what I'm trying to say is ways to measure it. Let's do a data-driven, example. Let's drive this whole thing from data. And you sit there and go, I have no idea how to give you good, reliable data that measures that artifact in a way that lets you make a good measurement out of it. The DNS seems to resist that completely. I don't know how long that took, Warren, but that's it.
We've still got time.
Cool.
We still have time. Hopefully there are questions. Maybe you covered everything. Yay.
Hey,
I'm in
question.
the queue.
There we go. Okay, you first.
Thanks, Jeff. I'm using, as always, at how the DNS is broken. So I will reveal the fact that in my graphs earlier for my internal tests, I didn't show the right-hand side of my graph where I measured, PCAP queries long beyond the point that my experiment had ended. And sure enough, there are little peaks for the same domain names long after I actually told RIPE to stop asking. So your notion that things run in a circle, I think Warren's, convinced me before that, some of that could be prefetching for caching and things like that, that some caches try and auto refresh some data, whether or not that's true. Shoot, there was something else that I was going to say, but I've forgotten it. So I'll get back in the queue if I remember.
Repeats are interesting.
Yeah.
Because in our measurement, we're seeding the world with unique DNS names, and we make care to put the time in the name. So when I see a repeat, I actually know how old it was. This was an ad that was delivered 2 years ago, because it's got the time in the name. And there's some interesting work in looking at ISP-based queries, it's coming from the same AS as the user, and queries that come from, say, Google or Cloudflare, open DNS names. Is the age profile the same? Or do we use open DNS resolvers for other purposes? There is a huge amount of log replay. Why? Because the DNS is free. And there's a lot of folk who capture bits of the DNS and just replay it again and again and again, which adds to the noise factor without adding to the signal factor. And it's remarkably hard to capture those replays unless you're putting the time in the query. So the problem, I suppose, inside all of this is when you're looking at queries, you have no idea why the query. It's not clear that this is a timeout, this is a replay, this is just, oh, it's a Wednesday, or it's a hammer aggressive cache refresh. It's really hard to tell. And then when you start to try and dissemble from that resultant log of queries, inferring behavior, you're in swampy ground is all I'm saying. It's not clear. Yeah.
Yeah, so I did remember the other thing I wanted to talk about, but following on in your discussion a second ago, I assume you know that somebody implemented a file system in DNS just by transferring bits, or maybe they did it in ping or something like that, because you have enough round trip time to get to the other side of the world that you can send packets out and expect it to get back. And as long as you keep repeating those packets, you actually don't need to ever store it on disk. But the other thing I was going to talk about, you mentioned, I believe you said that you were expecting sibling glue. And if that's the case, you really shouldn't be trusting sibling or parent glue. And there's a paper in NDSS that occurred 2 weeks ago. I saw the presentation for, showing the resolver percentages that were believing that you could cache poison your sibling or cache poison sometimes even your parent, which obviously is not good.
There is a much deeper issue here, and it actually refers to the DNS discovery process. In DNSSEC, answers are signed. The path to the answer is not. And very few folk actually do the distinction between NS records in the parent, NS records in the child, because only the child records are signed. The way it works out is that DNSSEC doesn't give a flying how you got the answer. It's just the answer that counts. And you kind of think about that going, is that right? Should I really care about how I learned the answer? And in some ways, I think I'm actually on the side of the existing DNSSEC approach. I don't care where I got the answer. If the signature says it's good, it's current, it's valid, I'm going to use it, and I don't care where I got it from. And if we're obsessing over the path and how the path was discovered, maybe we're wasting our time. And you go, well, that's just a Jeff comment. It strikes at the heart of the DELEG working group. Because if I really don't care how protected delegation is, it's the answer that counts. Why are we wasting our time trying to sign these records in a different way? It's a fascinating question. I don't have an answer, but I have an opinion.
Mr. Peter.
Thank you. Quite interesting measurements. I have two questions. The first question is, so I understand why you want to do the measurement with DNS only, like with the IPv6 name server only, and then return addresses for the web server in both address families. But can you explain again why you made the distinction with the gluelessness? I didn't understand what the upshot of that is. And the second question is, have you considered doing the same thing with CNAME, where the pixel host name is on an IPv6 name server only, but as a CNAME and points to some name that is on a name, yeah.
So the problem is in the web fetch issue, you don't get the web object. Is it because you couldn't do the DNS query or you didn't receive the DNS response? I can't tell, and if you got the response and you just got bored, I walked away, I'm going to count that as you don't do V6 in the DNS incorrectly. So I'm interested to learn, did you get the answer? Because what we found when doing the whole bunch of V6 transitions was often you could ask all you wanted, the answers didn't come because the filters were on incoming, not outgoing. And I was trying to isolate that factor of, did you receive the DNS answer? Glueless is one way of going, well, I can test that by doing a consequent query. If you did the next query, you got the answer. If you didn't do the next query, it's safe to assume you didn't get the answer. Why? Because it's really hard to interrupt the DNS. Once a recursive resolver has a problem, it mirrors the obsessive compulsive behavior of the programmers. It will not let it go until an eon of time has disappeared. Or in the case of Unbound, it will never let that question go. It's a question that deserves an answer forever. So that's what I was trying to test out. The CNAME, I haven't worked hard in CNAME. For a long time, CNAMEs were variously implemented. The whole synthesis of the CNAME and trying to understand the resolver behavior made my brain explode. It's probably a good idea and it's worth trying through, yes, but didn't naturally go there.
Job Snijders, BSD. I cannot help but wonder that you lament about the lack of TTL and there might be queries looping around forever. But then Peter points out there is the natural phenomena of bit flips. And I wonder, is this evidence of an intelligent design that we, in fact, do not see queries loop around forever and ever because eventually they'll hit some memory that flips a bit and it stops. I mean, we got to get some theological experts in that.
It is a fascinating question. We commonly say at the root service between 70 and I think Dwayne, if he's still here, said up to 90% of queries are NX domain. It's kind of, we're spending all this money building root servers where the answer is a really fast no. You could take a year to answer no. The answer's still no, what's the obsession? But this other question of, is there something waiting for the answer or is just the DNS talking to itself? And there is certainly an assumption, and our experiment tends to show that if you take a large number average, at least 40% of DNS queries are bullshit. No one's hanging around for an answer. It's not related to a user event in the recent past because those time signatures say, if it's in the first few seconds, it's a live user waiting. If it's beyond 30 seconds, we've all moved on with our lives. And the amount of queries that are as old as shit is disappointingly high. And the amount of engineering, time, and money we spend on the DNS to keep the bullshit answers coming quickly kind of strikes me as misplaced resource management. It's not worth it. Now, if only the DNS queries themselves say, here's how long it needs, and if you don't answer by then, give up and go home. That would be an interesting change in the DNS, probably better than DELEG, nudge, nudge, hint, hint.
Thanks.
All right, thank you.
Joel, we locked the queue, but Joel related, so.
I just wanted to add a data point to what Peter was asking. The main reason we didn't use CNAME is actually because the measurement originally was about the DNS itself. And switching A for CNAME didn't add any more reliability or extra signal to it. It actually would probably make it worse. Because again, the measurement was about the DNS, not about the web fetch. The web fetch was just a signal that if you got here, you obviously did this other thing before. But perhaps we can look at the many ways in which CNAMEs will be broken on the internet.
Oh, God. There comes another year of work of how broken is CNAMEs. And let's add DNAMEs as well,
Yeah, just to say what I meant. Apparently, one layer of indirection is needed anyway, because the first layer is the v6 only layer, and then the second layer is where you need the follow-up query, where you don't want to.
Because using the web is noisy. If I can put the whole thing into the DNS, I've got the obsessive behavior of resolvers that normally never let a question go until they resolve it.
Right. And so my question was only, why use the one indirection with the delegation that doesn't have glue and not use the other indirection with the CNAME? But I don't see that the CNAME in itself would necessarily make it more complex or less reliable than the approach he used.
Well,
always more work to do.
Thank you, everybody.
Thank you.
And many of you all have a long flight home during this time. Please think of what you're going to propose for the next IEPG meeting, DNS related, BGP related, other things related, whatever you have. And if you do not have a long flight home, you can do it over dinner. Thank you, everybody.
Goodbye, Warren. Thank you.
Bye, Wes. Bye, Jen. Thank you.
Sure, leave Lorenzo out.